In this video, we're going to begin one of the last major topics of the course, which is optimization in multivariate functions. We're going to start by distinguishing between local and global extrema. Fortunately, what we're going to see is similar to what we had in single variable calculus. Starting with local extrema, we consider that a function has a point that's a local max or min if, first off, the point is not on the boundary of the domain. So we're only looking for interior points here. And if this is the value at our point, the value of f or z at our point, that has to be as large as or larger than points nearby, the f or z value nearby. It captures then our idea that there might be a height of 10 somewhere, all the points nearby go below 10, but there might be some other maximum somewhere else in a single variable thing. This would point to, or this would be a local maximum, even though the function grows to larger values elsewhere. We're going to contrast that with global extrema on the next page. For identifying global extrema, it's the same thing. We still have our point and the neighboring points. Well, actually, it's not the neighboring points, it's all other possible points. So anywhere else in the domain, as long as we're lower or at most the same height as our point, then we call our point a global maximum. And we just reverse the inequality, talk about the lowest point if we're talking about minima. In practice, we are looking for global extrema. Say we're trying to find the best design, the best location, that would be a global extrema point. But the challenge is going to be that most of our tests to identify extrema are actually going to be more about local information. So we're going to have to think about what evidence is being provided when we do our calculations and determine whether we're talking about a local or a global extrema. We're now going to apply those definitions and ideas to a particular surface. We're going to define our surface by the function x squared plus y squared, which is our classic parabolic bowl shape. That's the shape where we have a parabola in one direction, and then it has circular symmetry, so we get a bowl shape like that. With that in mind, we can then draw our contour diagrams, but note that we're going to be limiting ourselves specifically to this domain from x equals -2 to 2, so here to here, and the square then bounded at the top and bottom by 2 and 2, -2 and 2 for y as well. We're going to get our other perspective on this surface by drawing a contour diagram, and we're just going to use the integer heights 0, 1, and so on. We know how to do this fairly easily now. We pick our z value, and then we sub that in for the function value and see what shape we get. In this case here, if we have the x squared plus y squared equals 0, that's a single point at 0, 0. So that's a single dot on the coordinates here at height 0. If we move up one notch, we go to z equals 1, that gives us 1 equals x squared plus y squared, and that of course is a circle, again, x squared plus y squared, but now with radius. Well, remember this side here is the square of the radius, so the radius is square root of 1. Well, fortunately that's just 1 as well. So we're going to have a circle like so, and that is at height 1. And we can start to see the pattern. We choose z equals 2. We're going to have 2 equals x squared plus y squared. That's a circle again, centered at the origin, with radius of square root of 2. Next up is z equals 2. That gives us 2 equals x squared plus y squared to define the contour, and that is a circle with radius square root of 2. Perfect. So you start to see the pattern emerging here. Square root of 2 is around 1.4. And so we have a height of 2 for that contour. And then we can start doing associations from here on in. If we do z equals 3, it's going to be a circle with radius root 3. If we do z equals 4, we're going to get a circle with radius root 4. But that is just 2. Let's do those two next. So a contour here at height 3. then a contour at height 4. That just touches on the boundaries here. And then we get something interesting happening in the relationship between our constraints, the limits of the region we're looking at, and the contours. We can go higher with z equals 5, and that of course will be a circle of square root of 5. And that will be a circle that goes a little bit further out. It has radius of 2.23, so it started out here, but it would eventually cross back into the domain that we are looking at. So I'll put the label on this end. And we can actually see there's going to be contours higher and higher until we get to z equals 8. At that point, that's a circle with radius root 8. Well, if we take a look at the distance from the center here out to here, that's going to be 2 squared plus 2 squared, that's 4, that's 8. Root 8 is going to be exactly the distance to that corner. And we're going to see the same pattern here, where we're at height 8, 7, 6, and 5. And then we consider the interaction between our domain and those contours. That's going to be our next step, is to look for where the maxima are. Before we do that, though, we're just going to insert a quick review where we look at the gradient vector at several points. So in this entire surface, we should be able to pick any point we like, let's say here. And if we pick that point, there'll be a gradient vector automatically defined, and the gradient vector will point in the direction of the steepest uphill path. So at this point here, we're at, if we follow the contour around, we're at height 3, but we're going to be directed towards height 4. And there's a subtext, the steepest uphill direction will be perpendicular to the contours, specifically the contour that we're on. So if we're here, I could go this way or that way, but we're pointing in the uphill of those two options. So of the two perpendicular directions, the gradient's going to point that way. And that's actually going to give us an indication for what happens next. If we pick elements that are close to the corners, we can see where we should go to go higher on the graph. We should go towards the corners here. So that's the gradient vector, and it will play a role a little later in optimization. But for now that we have the entire contour diagram, we can actually identify the global max and mins of that function limited to the domain that we drew. Let's take a look at that. If we look at all the heights, 4, 3, 2, 1, comes down to 0, the global min jumps out pretty quickly. It's at the origin, 0, 0, and the height there is f equals 0. All right. What about maxima? Well, as we just pointed out, the gradient pushes us towards the boundary and then actually keep pushing us down if we want to stay inside the fence line. But what we see with the corners is if we keep going up and up and up, the highest we can get while staying within these borders are the 4 corners, all which have height 8. They're all in the same circle, and they all have the same height. I could go to the border somewhere else, but we can see that that would have a lower height, like a height of 7. If we want to go the highest, absolute highest, global highest, we'd have to go right into the corners. So for our global maxes, those are going to be at multiple locations, at 2, 2, at negative 2, 2, at 2, negative 2, and negative 2, negative 2. That's all the mixes and matches. All of those have height f equals 8. And on this domain, everywhere we look, the function is going to be less than or equal to 8 on the domain. Perfect. Now there's an interesting idea that comes out of this. Notice the 4 boundary points are the global maxima, and we'd say those are not local maxima or minima because they're on the boundary. Going back 2 more slides actually. we would define local max and mins as points that are not on the boundary. So let's add one more specificity here. These are global but not local extrema. And the reason we say that is because we want to contrast those with the point in the middle here. This point at the center is lower than all the points nearby. This point not so much, because if we count the domain outside, then we would go higher than 8. But here, 0 is the absolute lowest point we can get out of any of the neighbors. And so it is a local minimum. And so that makes it worthy of studying for a different reason. And one of the things that we can say about that point is something about its gradient. If you think of the direction of steepest uphill ascent from that point, well, it'll have to be the direction perpendicular to the contour. But the contour is a dot. How can I be perpendicular to a dot? Well, you can't. That can only happen. I can only have a vector with no direction if the vector we're talking about is the 0 vector. So the gradient at the global minimum is the 0 vector, and remember that that translates to the x derivative y derivative equals the 0 vector, or, hey, what happens at maxima and minima? The derivative equals 0. So in this case here, we're going to tie the gradient back to the derivatives equaling 0 at local minima. And that's going to be where we head a little later in the course.